everyone. This speaker, as you can see, is from ICTS-TIFR. This is PhD Professor CHOWDHURY, and today we shall be talking on principle of holography of information. And as you can see from the title of this talk, the interests are in AHEP, holography, and quantum information theory. CHANDRAMOULI. Thank you very much.
You have to turn it on. You have to turn it on.
Okay. Am I audible or? Yes. Yes. Okay. So thank you very much for having me here. I'll be as described, I'll be talking about something called the principle of holography of information, and is this better? Is it okay? Or? Is this fine? Okay, okay. Great. So I'll be talking about principle of holography of information. So I should acknowledge my collaborators. Large part of this work was done with my advisor, Subrat, and Olga Victor. Olga is a postdoc at Dept now, and Victor is a postdoc at ICTS. So everything that I'm going to talk about can be found in these three papers. So the first part of the talk will be on something called the physical protocol, which I'll explain what it is, and the next part will be on the video integration. Okay, so let me start by motivating what I'm going to talk about. So in this work, what we've explored is the unusual localization of information in the theory of quantum gravity. So I'll actually not be making any reference to a particular theory of quantum gravity. In fact, I'm not anything from string theory. So what we try and discuss is the holographic nature of quantum gravity. I'll explain what I mean by quantum gravity in the next few slides. And what I'll try and emphasize is on how quantum gravity stores information differently from that of classical gravity or other gauge theories. Okay? And the notion of information that I'm going to talk about will be different from the usual notions of quantum information. But I'll have a very simple description of what I mean by information. Okay, so let me actually start the result. Start by stating the result. So if you consider any theory in ADS, then what the principle of holography of information states is that if you have a wave function in the bulk with some profile, in this context it's a profile that has some color of a rainbow, then what this principle states is that all information about this can be obtained from the boundary of the Cauchy slice. So what I've tried to draw here is a Cauchy slice which has information in some manner, and all the information can also be found at the boundary in some form or the other, which is what I've tried to depict on the right side. So the more general statement is that all information present in the bulk of a Cauchy slice is also present at its boundary. Now, of course, from ADS-CFT, this principle is kind of obvious, but in order to prove this, I'll not use any ADS-CFT. What may not be obvious is that a version of this is also established for flat space. So this was first done in 2020 by these set of authors, where they argued that all information about a state which is composed of massless excitations in the bulk, that is available at the red slice. So what I tried to draw in this figure is the Penrose diagram of flat space, and this in particular is this part of the diagram is infinity. And what these authors argued was that all information about massless particles, which you would anyway expect to be found at pole of non-infinity, is actually available in this thin time band, which is basically near Spranker's minus. There's a similar statement for also the past version. That's okay, so let me give a toy example of how this thing works. So firstly, you can consider two different excitations. So like this is a very simple toy model. you just have two states which of this kind, where phi1 is a field with some flavor and phi2 is a field with a different flavor. But they are built by using the same smearing function. So the smearing function is f of r, and lambda is some perturbation parameter. So this is basically some unitary operator acting on the vacuum state. In this diagram of the depicted in yes. So field phi1 is basically this red colored sphere, and phi2 is basically the blue colored sphere, and they have the same distribution. So what I'll prove for you is that if you measure this particular correlation function, which is the expectation value of h and the boundary value of the scalar field in the state psi, you'll be able to recover f of r. So I should emphasize that since this entire thing is done in the theory of gravity, Hamiltonian is a boundary term, which I'll come back to later in the second part of the talk, but I'm just going to use the fact that the Hamiltonian is a boundary term. Okay.
The f over function is depend on what? That f over smearing function.
Yeah.
It depends on what? What is the smearing function?
It can be anything as long as it's some local smearing function. So, for example, it could have been e power minus r squared. Anything else is it want to have. So.
This you are considering in a constant time slice.
Good. So I'll actually be considering a thin time band, which I'll emphasize, but it's basically a time band which has an infinitesimal loop. You can go with as long as you like, but not zero. By the way, feel free to interrupt at any point. Okay. Any other questions at this point? Okay, great. So, like I already mentioned, what you find is that if you measure these correlation functions, that is the expectation value of h, the boundary value of the scalar field, let's say for the flavored one case, in the state psi1, or if you measure HO2 in the state psi2, and you work in order lambda, then you would recover the function of r. This might sound mysterious at first. I'll try and demonstrate a simple proof for it in the next page. However, how would you know that you're not working with the right state? So that one way to do that is to measure the expectation value of h and oj, for example, in the state psi I, where j is not 4. So in a sense, you could measure HO2 in the state psi1 and you just get 0. So therefore, by measuring such correlation functions in a thin time band on the boundary, you can extract information about the state. Now, this would not be possible in a theory of classical GR. This is simply because in classical GR, you would only gain information about the total conserved charge, the total energy, the total angular momentum, any other conserved charge you have. But in the theory of quantum gravity, you are allowed to measure correlation functions, and not just the expectation value of a particular object. So even in this toy example, you see that how information can be delocalized in the theory of gravity in a non-trivial manner. I mean, this of course was a toy example, but I'll be giving you examples of more complicated states later. Okay.
That the diagram you drew in the previous slide, is that any particular theory of gravity, or you are considering some?
No, I will reference to
With the general theory of gravity.
any general theory of gravity. Eventually, in the wheeler to bit part, I'll be illustrating to extent here. But as of now, all I'll be like you'll see what I use in the proof. All I'll be needing is that h is a boundary. It's some operator which goes on the boundary, which is true in general for any kind of gravity. Of course, it's most well defined for extended gravity. Okay, so let me just give a proof for the reconstruction. This is the only slide that I have any complicated information. So, like I said, let's say you consider this particular state, which is psi of t naught, which is built by exciting this field phi of t naught, which is a function of r. You act with this unitary of the vacuum. And what you're going to measure is the expectation value of h and the boundary value of this field phi. So the way O is defined is basically by taking the r tends to infinity limit phi, and you have to move slightly away from P naught, and you can make epsilon as small as u naught. So to measure this expectation value in the state side. And the way we would do it is that we just expand, we basically expand this to order lambda. So, for example, you consider this particular correlator, which is the same thing as this guy, and you replace what psi was by the unit fields acting on the vacuum state, and you expand in order lambda, so you just get this equation up to, and you retain terms up to the first order. So you basically end up with this. I have omitted lambda from this step, but it's only non-trivial term you get in order lambda. Now the trick is that you use the fact that H acting on vacuum is zero. You can renormalize H in that way, and so this equation would basically turn to a commutator you can H know, which you all know is the conjugate moment of a however, this guy is simply the time derivative of the multiple commutator. Now, once you have this expression, what you can do is you can expand this last expression in the Taylor series of epsilon, and that would allow you to extract the moments of the function alpha n, or the distribution function that depends on f of r. Since you can extract the moments in an arbitrary order, in principle you've got f of r up to whatever order you allow yourself to extract. This is the proof. Okay, any questions on this?
So O is just defined at the boundary.
Yes. So in fact, O is defined on this way. It's literally like r plus infinity r by delta, where delta is the it's basically the conformal dimension, but you can also find that by only working with the bulk. So all I'm doing here is I'm defining these fields by solving for the wave equation in ADX and using directional boundary conditions. That will tell you that the field goes as 1 by r by delta.
Why is H there in the correlation function at all?
Because I need H for anything I do. Since H is like measuring the energy. Like in some sense, it brings energy into the system, and I'll explain a lot about why I need energy in this entire physical protocol part. But in here, of course, H is giving us the bulk boundary propagator. So I don't know how to make a protocol work without using H. Okay. So let me now try and focus on why it would only work in a theory of gravity and not in any other theory. So, for example, if you consider a local field like a scalar field theory, and you don't have any gravitational field in the system, or any gravitational constraints or whatever, then notice that you would not be able to distinguish a state psi from the state u bulk acting on psi by only making boundary measurements. And this is simply because any bulk unitary would commute with any boundary operator, simply from microcausality, because these are space-like, they would just commute. So, which means that if you restrict ourselves to making measurements of this kind, which is basically measuring the expectation value of a boundary operator in some state psi, then you would not be able to distinguish the value of this result from the value of this result. So instead of psi, you have u bulk acting on psi, because these both would simply commute and you would have a u and u1. This counter example would not work in gravity because these kind of commutators are non-zero in gravity. However, these kind of commutators are also non-zero in gauge theory to some extent, but there you can construct u bulk out of gauge invariant operators. For example, FPNU, FPNU. For example of a bulk unitary like this is simply this guy. And again, this counter example would fail in gravity because there are no gauge invariant, local gauge invariant operators in gravity. Any kind of gauge invariant operator you try to make is always going to be non-trivial, at least in the way we are formulating. There are some caveats to the statement for very recent work by Kyriakos Papadimos, but we can discuss that after talking. If you're interested. In any case, the summary of this slide is that you will not be able to make this trick work, this trick of reconstruction work, in theories which do not have gravity. Okay. This has a formal statement that says that there are no split states in quantum gravity. Split states in general is defined in a slightly different way. In case that terminology is familiar to you, this is what I mean in that way. But you don't need to go into the definition. And for this, I want to emphasize that we are not only allowing ourselves to measure the energy, but also correlation functions involving energy, which is what you cannot do in classical gravity. Classical gravity, there's no meaning of correlation functions. That is, you don't have a propagator when you have h bar equal to 0. Okay. And in here, we are doing this because in general the bulk state need not be in an energy ion state. Hence, if this kind of a measurement is not enough to be outside, we use this kind of measurement, which demonstration of that is something I've already shown very first. Okay, any questions before I move on to the bulk?
So are we not doing just quantum field theory in plot space?
No, we are not doing quantum field.
So what is that state basically which you wrote like F starting any state?
This guy?
Yes. What is the vacuum here?
Oh, the vacuum is your usual ADS vacuum. The place with this NBADs.
So you're assuming that you have quantized the gravity here.
I'm going to quantize gravity later on, first order of perturbation theory. I won't be able to quantize gravity to all orders of perturbation theory. But in this case, of course, I'm assuming that you can obtain H as a quantum operator. So, and that you can do at even first order perturbation theory.
That's all right, but phi is not simply a scalar field.
Phi is a scalar.
So, and what is the bulk there? And bulk is just classical gravity.
Bulk is ADS. So,
Classical.
Bulk, I mean, okay, the thing is, any kind of quantum excitation that I'm going to talk about, even for gravity, when we talk about it in a perturbation, the perturbator fashion. So, just to illustrate, I'll come back to this equation later, but all I mean is that any kind of Gij that I write is always going to be the ADS metric plus any perturbator excitation. And this H that I write down is something that you can measure just from this small H. In fact, in ADS and what's called the fundamental gauge.
So when you're saying quantum gravity, it means linearized quantum gravity.
So
you're
low energy quantum gravity. Low energy, exactly.
Not only low energy, because when you're expanding about this thing, about this background, this HIG is linear, it's a linear perturbation.
Oh, actually,
linearized kind of quantum gravity that you are formulating.
I could have written kappa square as well, but it's not exactly linear because I also allow my graviton. I also allow for gravitons, which can have kinetic energy. So they can have a pi square. But the important thing is that energy as such can be obtained just from this expression. That's all I need. That's the only place where the quantum part of gravity is not. Of course, I'm assuming that this vacuum, whatever I'm writing down, coincides with the vacuum of the fluid.
So what you're doing is, first of all, you have a metric G, right? So that is classical, and then you're expanding it, and then that is what we do in linearized classical gravity also, when we do gravitational waves.
Sure.
So you have this classical gravitational wave kind of thing, but this is now expanded about some ADS kind of background.
It can be in flat space.
Yeah, you can do it in flat space. But now what you are doing is, once you have done this, then you are postulating that you are classical this, you are now elevating everything to quantum status. So you are saying that these are operators.
Yes.
So
including HIG.
This HIG is the thing that you are basically trying to quantize. You will later on quantize.
Eventually, it's true. Yeah.
Then you will get the graviton picture. Otherwise, there is no graviton picture. It is gravitational wave.
I completely agree. Yeah. Which is why it's not QFT in curved space. Because in curved space time, you don't assume that HIG itself is quantized.
Yeah. It's not QFT in curved space time. QFT in curved space time, you only quantize the matter fields. Gravity is completely classical. But here you are quantizing, but this is in the linearized quantum gravity domain. And the graviton picture that you are getting also, that is also in the, see, what I have been understanding that graviton, I cannot even say that it is the quanta of quantum gravity, the quanta of linearized quantum gravity. Because
that of course depends on what you call it.
Because you don't know the full quantum, as you also mentioned, that you are doing quantum gravity only for derivative. So the full gravity theory is not, quantum gravity theory is not true. And therefore there is no graviton also. I cannot say that there is the graviton is the quanta of full graviton quantum gravity theory. It is only the quanta of linearized quantum gravity theory. Okay, fine, sure. It should be like that. And your H that you are writing, this is the Hamiltonian that you have constructed out of the H, small h.
That's exactly. Yeah, that's all these things. Right. But I agree with all these things. Like I said, the only information that I would need is really the fact that H and O give you pi.
Yeah, that is.
In fact, in this particular thing, as long as I agree that in general you should define your vacuum very non-perturbative fashion, so on, which you can do using the path, like assuming that gravitational part of converges, which it doesn't. But eventually, as long as H and O completely pi, which of course is true in perturbation theory, but in non-perturbation theory, in non-perturbative level, we don't know how to read. Like I said, one of the important things of where gravity is coming into the picture is really the fact that H is a boundary term. We would not have been able to do this using scalar. Okay, great. Any other questions?
Now, as far as I understand, gravity is coming through the fact that it is coming to H.
I mean, the fact that H is a boundary term is one case of gravity. That's right. And also, you know, in order to make these contradictions go away. I'm using the fact that space-like operators don't compute in the theory.
Yeah, that is fine. Yeah.
Also, they can't have any flow behavior. Both of these are important cases for gravity. Okay. Okay, that's great. Keep asking questions. So now let me explain what I mean by the physical protocol, which is basically again, a perturbative and sort of a recursive procedure by which we can obtain not just information about that special state which I showed you in the toy example, but for any general class of states. Okay. So now this is the line on the top is basically the statement of philosophy that I already made before. So just to reiterate, if you have flat space, this will be more clearly established for 4 dimensions, but everything that I'm saying would in principle go through high dimensions, at least for high even dimensions. We can have a discussion on why I'm saying that for now. Like we can have the discussion later. Now notice that if you just have massless excitation, then just from causality, all information about massless excitations would be naturally present as prime plus. That's where massless excitations go. What principle of holography of information says is that the information which is available as tri class is also available at its past boundary, which is basically a cut near tri distance. Now I'll try and prove why I'm saying that.
So this red slice is where actually in this conformal boundary.
That's right.
But see the conformal boundary there should be there also, right? Yeah.
Yeah, good. So actually, this statement has another avatar, which is basically that I've only drawn the picture the top of the canvas diagram. All information is available either here or here. Just prime minus plus and this one is minus. What I think Sugat and company now trying to do is try to have a statement that says that everything can also be obtained from I naught. And also massive particles, but that's not established. Okay, everything that I'm going to talk about for the upper part of the canvas diagram is also proven below. It's interesting. So I should mention one caveat in all of this. Although this principle is well established, the principle of holography for non-infinity is established in for like very general sort of states. In this part that I'm going to describe next, which is this physical protocol, I'm going to totally ignore the presence of supertranslation factor. That's mostly because we have not been able to formulate it very cleanly how we can describe the physical protocol to extract that. But if you do allow yourself to have states which are built on different supertranslation backward, then even then you can write this. Anyway, so what is that caveat? Let me now try and describe the physical protocol to decode the state psi. Of course, by physical protocol, I don't mean something we can do in real world, but something which at least super observers can do. So, if you consider a state which is expanded as follows, this notation might be slightly cryptic, but these dotted stuff is the usual thing of what we call normal ordering, that is, we push all the creation operators to the left. And these nearing functions Gn are the ones which the observers have to determine. Okay. So, in a sense, this the state is expanded as states which are formed out of one particle, two particles, three particles, and so on. And these GNs are smeared across all of spectra. They are just sufficiently local, smeared across all of spectra. And what I'll prove to you, or what I'll argue for in the next 3 slides, is that by making a projected measurement on this in this red region, which is something of this form, I'll explain what these are. The observers can decode Gn in a sieve-like manner. So what I mean is that the observers who are spread across stripe plus minus are given two kinds of paths. So they're allowed to interact with the state by acting on it with a unitary operator, which is what you'd expect from perturbation theory, that you can add an interaction happening into the system, and the way that you modify the state is basically through the action of the unitary operator, which is of course localized at stripe plus minus, both of these unitaries. And then they are allowed to measure the energy of the state. And that's how the projector comes in. So this P naught is the projector onto the vacuum state, as I explained in the next slide. And then what I'll argue for you is that by making measurements of this kind, they'll be able to decode the functions Gn. And like I said, the observers will be decoding the functions Gn in a sieve-like manner, by which I mean they have to decode G1 before decoding G2, and so on and so forth. Okay, so in all of this, I'm going to assume that the bond rule is valid, whatever the and that's because the observers will be asking this following question. But what is the frequency with which we get 0 by measuring the energy of the state U1 side? What is necessary according to any state? And the answer to this question in a quite literal sense is this expression. Okay. Where U1 is the unitary that the observers act with. It's some function like this. Where this f of r is up to the observers to tune. Fortunately, use notations now where f of r is up to the observers to tune, and g of r is the one that we tune, right? O of r are the same field operators of the and these are basically the value of the boundary value of the field. And this unitary is localized as stripe plus minus, and P0 is the projector under the vacuum state. I should also mention that here I've just done everything for one single flavor, but everything can be generalized to any flavor, any stream. Still work. As long as you maintain the assumptions of okay. So the way you would make it work is that you expand this correlation function to order f. So they obtain the value of this correlation function by asking this physical question, which is literally measuring the energy of this state and n number of times and seeing the frequency. And once they expand the state again to order hyperration of n square, they would basically get this result. Now notice that by choosing the phase of psi appropriately, that you just choose the phase of psi to be something which allows you to solve this equation by taking square root on both sides. That would allow you to determine the function g1r in terms of f of r. And the way they would do that is exactly similar to what I described at the beginning of that by example section, that you would again be getting a boundary propagator and expanding n epsilon and so on and so forth. Eventually, the upshot of this procedure is that by fixing the phase of psi, they would be able to determine what. By choosing the phase of psi to be whatever they want, they'll be able to determine the function g1. Is that okay?
What was the function?
So the state psi is expanded in terms of this, and gn's are the functions which the observers have to determine. So what I'm saying here is that these are scaling functions which are located all across spectrums. And what I'm saying is observers who are located at stripe plus minus will make certain measurements and decode those functions. Even though Gn has support in all over stripe plus minus, but the observers are still localized to stripe plus. Sorry, I apologize. Gn has support all across stripe plus, but the observers are localized to stripe plus. And they're able to do this, of course, because again, energy in this case, which is given by an integral of the 1D mass, which is roughly something like this again, is an operator which is also located in stripe plus minus. So that's why they're able to measure the energy of the state. Okay, so the next part of the protocol will also follow a very similar philosophy. So, for example, I've told you how they can measure the function G1. In order to measure G2, they have to simply modify the state by acting on it with an unitary U2, which is expanded in this form, and they'll be able to obtain G2 now up to a phase factor, because the phase was already fixed in the previous measurement. You can only fix the overall phase of the state once. Now, this phase factor can be fixed by making this sort of a measurement, where they modify the state by acting with two unitaries. In this case, it's between U2 and U1. And you just slightly play around with this equation. And what you can show is that you can fix the function theta. You can fix the number theta. Now, the other functions Gn can first can be worked out in a similar procedure. If you first measure this, and then if you fix the phase by measuring this. And like I emphasized before, this procedure has to be performed in the same procedure, which means that you have to first determine Gn minus 1 before finding Gn. This entire procedure will be performed in ADS, which is what was first done in this paper in 2020. But there we had a more cryptic way of doing it, where we just said that the basis state is chosen using or is found using the Nishida theorem. But in this case, I don't need to invoke the Nishida theorem, but I gave you an example of how that would work. Okay. So one last point about this protocol business is that there's no violation of causality in this entire process because of this one fact. Now, here again, not ADS, but all of this is also valid infinity. It's basically because the observer is located on this skin time band, which is true, and then they are making the measurement of an energy, which is determined by the fluctuations of n00, and therefore they need to be spread across all of omega, because this integral, this integral is basically an integral over omega. So in 4 dimensions, it's an integral over theta phi. And therefore the observer should be located all across this circle. And each of them will be measuring a small part of what n00 is. So they'll be able to measure the value of n00 at their own location on the celestial sphere. And in order to assimilate the data, which basically means in order to do the integral, they need to go out of the time band and communicate with each other. That in general would take more than light crossing time. So even though information is formally localized in this region, there's no way to access the information before light actually ends up reaching the boundary, and hence there's no violation of causality. Okay, any more questions before I move on to part 2?
If your time permits, could you please tell that how this projection operator actually works? I mean, the way you are obtaining the G1 or G2.
Oh.
So this is all like a P0 is sandwiched between dagger and U.
Yeah.
Just briefly, if you can just.
Yeah, sure.
I mean, if your time permits.
How much time do you have left?
20 minutes. Little more than 20 minutes.
Okay, that's good. So anyway, so just to just to demonstrate this, so this was U1 dagger P0, U1 side. That where the side was made up of states like this. So here the side had integral over phi and G.
This is how your G1 is defined for this expression of U1 dagger P0 to 1.
Yeah.
Basically giving you the G.
No.
Okay.
I mean, this will allow me to determine G1,
Okay.
but the statement is that the state psi itself is expanded like this. There's a G1, there's a G2, then there's phi phi, there's G3, phi phi, and so on. So the state, so these G1s are up to whatever, maybe this is for the observers is basically God given, and the observers have to determine what God gave them, so they have to determine what G is. And the way it would work is, just all I've done in going from this step to this step is literally just reaching what side was. Then I have U1 dagger P0 side. And the way P0 comes in is it's basically this guy. And I just use the fact that the creation operators are highly vacuum. And I'll expand to the order F. If I expand to the order F, I'll just be done with this. Okay, so now let me move to the second part of the talk.
But this expression that you have, this is basically equal to this. This is the probability of getting uh, the value 0 if you measure energy, right? And that expression is this.
Yeah, so I'm saying that
When you plug in all the expressions for get psi and everything,
yeah,
that
that's
expression. But how, as you say that from this expression you are able to fix G1. So by that what I understand is that you somehow know the left hand side,
yes,
and then this is an integral equation kind of,
absolutely,
and then you are determining G1.
absolutely.
But the question is, if that is what I have understood is correct, then the question is this left hand side that you have, you should know it a priori from before.
So the left hand side is the
how
answer
do
to
you know
this
the-
question.
Huh?
Left hand side is the answer to this question. What is the frequency of
Okay,
measuring zero?
so what you are assuming is that you know that value.
Is by which I mean I'm assuming also the bond rules. So there are some observers who are located at plus minus, or in the case of
I
A,
think Pushpita's question was something else. What I understood is that probably you are trying to understand is that why is the probability given by that expression? Is it by
I was
this side?
just asking that how this projection operator actually giving
That's
this expression.
yeah. So what she wanted to ask is that why is this P0? This is the projection operator, take 0 plus 0. When you sandwich it between these two states, why is it equal to the probability of measuring energy 0? So that is actually straightforward because you just put it as he has mentioned this bond rule. Just if you do it, you will get P1 get psi plus 0 mod square. So that is why.
yeah.
So you are assuming that you know the left hand side somehow from before, and then you will find out G1.
True. And what I'm going to assume is that the observers
Have measured and got that value.
absolutely. So like I said, they are given two powers, which was to modify the state, which they have already done, and then measure the energy of whatever modified state is. So they know the value of what they're calling. That is literally a value of this. And the way P0, at least mathematically, the way P0 comes is in basically in order to make this simplification of A acting on 0. There's one more way in which you can define P0 mathematically, which is often useful, which is to think of this as the limit of alpha tends to infinity e power minus alpha.
What is another thing? What is important is that then you are tacitly assuming that the bond rule will be valid.
That's an assumption.
Assumption. So it turns out that in some quantum gravity theory, bond rule gets violated.
Yeah, that theory.
Then it will not work.
Good.
So it is like a postulate. You are assuming that bond rule is
true. I'm assuming the bond rule is valid. That's true. So okay, we can discuss more on what will happen if there is without the bond rule. But there
okay. That also you have figured out. What will happen?
Yeah, I can tell you.
Okay.
Yeah. So there I'll not be making these projective measurements, but I'll just be measuring correlation. But here I wanted to make it projective because that was more accessible to the physical observer. And that's where the physical name was. There's really nothing practical about this. Great. Thanks very much for these questions. Any more questions? Yes.
Don't worry about your time.
Okay. Great. Okay, great. So now let me talk about let me begin the second part of the talk, which is about basically describing that the principle of not perfect information, but for states which satisfy a particular equation, which I just want to. So this is a statement that I've already used many number of times, which is that in gravity, energy can be measured from the boundary. And the easiest way to see this is to perform an ADM decomposition for the Hamiltonian operator. So that reduces to a set of three terms, where two of them are integrals over the bulk part of the Cauchy slice. The other term is integral over the boundary value of the fields. So these bulk terms have some long expressions which are not important for the talk, but I've just flashed them here. And you have to treat a theory like this in the formalism that Dirac taught us, which is to basically use the constraint formalism. And you've got some primary constraints and secondary constraints to the theory, but if you don't go into the details, what just comes out of it is that the bulk part of the Hamiltonian is actually set to 0. And The full Hamiltonian is therefore just a boundary term, which is some expression that I'll show later. Now, one place where all of this is like easiest to see is basically QED, where you know that the conserved charge can be expressed as a boundary. This is exactly similar to that. Charge, like energy, is like the charge of gravity, and that's essentially a boundary details. It's a property of a gauge theory, gauge theory, which is masses. Anyway, so you have to, like, these are classical equations, which are analogous to the Einstein equations. Um, you have to uplift these two in order to do quantum theory of effect. You have to uplift these two quantum mechanics, and then you have to uplift what pi's and pi's are to your quantum operators. So pi basically becomes the derivative of d by dh, and then you basically get some functional equations which looks like this. And you can think of these as the Schrodinger equation for gravity. This equation in particular, the one satisfied by the Hamiltonian constraint, is known as the Wheeler-Dewitt equation. This guy is the Hamiltonian constraint. And the analogous equation in Gauss, the analogous equation in electromagnetism is the Gauss law, which all of you have seen already, which is basically the equation like this, where the gauge invariance of the wave function is implicit in this equation, and it states that the electric field at some point is determined by the charge density. And these equations are therefore known as the pointwise constraint, because these are valid at all points. Okay. Just these equations in gravity are simply generalization. Okay. Now these equations are extremely hard to solve in general. I don't know of any closed form solution of these other than 2 dimensions. So what we try to do is solve these perturbatively in Papa, which I'm obviously doing. So, like I already said, we expand the metric perturbatively, and once you have that, you can similarly expand the constraints. And it's also useful to decompose Hij in terms of its longitudinal and transverse modes. These formulas are not so important, but the only thing that will be important later on is that one is the longitudinal part, the other is the transverse part. And I further decompose the transverse part into a term which only has the trace of it, the other term which is traceless. Okay, so TT stands for transverse traceless. Okay. Now, unfortunately, even the pointwise constraint were very difficult to solve in perturbation theory. Although we have a solution, at least the leading model, which I'll flash at the end. But in order to get there, it was easier for us to analyze what we call the integrated constraint. Again, the simple version of integrated constraint in electromagnetism is simply this expression, where the value of the electric flux at the boundary, which is E.S, is obtained by the charge inside. Okay. So when you apply this to QED, you would basically have to act on this, act with this on the wave function inside. There's a similar equation in gravity which just says that the value of energy flux on the boundary, or the energy, is equal to the expression of the stress tensor inside, and the expression for energy flux looks like some long expression like this. And if you choose your lapse shift appropriately in the Fermi-Graham gauge, you just end up with this expression. And in the body gauge, you would end up with an integral over the body mass. Okay, and the energy of the bulk is basically this guy. So this part is whatever I'm calling graviton, is the transverse traceless part of the fluctuation, that's quadratic in it, and the other part is any other matter field that you might have. In this work, we've only done matter which is minimally coupled, but okay. Okay, any questions for now? Just a second. All I've done is written our usual expressions for energy or activity and just acted on that, acted with them on the wave function. So whatever physical wave function you have to define have to satisfy this equation, and by physical I just mean to satisfy the gauge invariance formulas. Okay. So this integrated constraint at least can be solved, solved very easily in perturbation theory. And psi I, for example, which is the solution to this equation, would depend on HTT, the transverse traceless mode, any kind of matter you have. The formulas we have written in the paper, of course, that's the details are not important, and the value of the field at the boundary. And you can solve the usual way to do propagation theory. And the solutions look like this. So the left hand side of equation 8 is basically what solves equation 7. And the right hand side means this. Psi f are Fox-Fix wave functions, right? Which I mean you get them out of your vacuum wave functions, as shown here, by acting with creation operators. And they are at some fixed energy E, which is what this tensor product means. So use the fact that in ADS, the energy eigenstates are discrete, which is what you basically get if you study a problem in a box. You solve for a wave function in a box, you use the Richter boundary conditions, then you end up with discrete set of states, which is okay, great. Again, these exact forms are not important, but just notice that they are quadratic and quadratic. Right. So now the constraints, what they're showing you is that the dynamical degree of freedom of the wave function, in this case the wave function L, are correlated with the value of the boundary Hamiltonian, which is what this expression is showing you. And in principle, you can also solve for the pointwise constraints to order kappa. The expression was kind of horrendous, so not to be here. But the way it's modified from the Fox-Fix solution is just that there's a phase factor depending on your longitudinal component that comes in. So it's basically an expression. This time, e power I kappa s is simply 1 plus I kappa s. I didn't have to write this e power I kappa s, but this is only valid in order kappa. Okay, so like I said, we are only working with solutions with the propagation theory for kappa, but the exact form is not going to be essential for this. Okay, now I'll go on to the proof of how holography comes in. I started the topic. So any questions on this one? Okay, great.
What is S in the
It's
the I kappa S?
Yeah, the S is some very horrible function. It's a function which I think is yeah. I don't remember the form exactly. It's not really. Because e power I kappa s could have just been written as 1 plus I kappa s. But the thing is that this equation solves your pointwise constraint, which was the equation we started with at the first order equation.
So you have managed to solve the relativity equation.
To just the first order.
The first one.
To the first one. I mean, in fact, Kuchar had already done large part for us in that space. So we used a lot of his results from 1970.
And you need the solution for that in order to determine the energy of the first one.
Precisely.
Because you will act with the H boundary operator on this side and you will get the energy.
That's exactly what I'm doing. So again, the details of the solution are not going to be important, but it's just formally important that H acting on this guy gives you the energy. Okay, great. So now let me explain the final proof of holography. Okay, this is the proof. Until now, only talked about states, but could have also like would have demonstrated because of the physical protocol was for pure states. But this proof of holography works for general mixed states as well. So just consider any mixed state which is expanded in terms of basis functions that solve the Wheeler-Wheeler equation. So the psi e's are basically functions which solve constraints. A's are labels which cater to other degeneracy levels you might have, and C's are the functions that will C's are functions of E, E prime, and so on that will be determined in density matrix. And what I'm going to argue for you in on the slide is that if you impose the fact that the expectation value of this operator, which is consisting of the boundary value of the Hamiltonian and the boundary value of other fields, coincide up to some arbitrary values of m, e, and n. This arbitrary means up to order 1 by kappa. For two different density matrices psi 1 and psi 2 in this thin timeline, then C1 must be equal to C2. I mean, another way of saying the statement for the pure states would have been this. So we are just expanding states like usual way you would, where these satisfy your constraints. Sorry, solve them. What I'm saying is if you have two states, psi1 and psi2, psi1 and psi2 and another c2, and you can find that the expectation value of h and other boundary operators agree for these two states in this small time, in this case it's ds, and this n time band into epsilon. If you find that these coordinators agree, then psi1 must be equal to psi2. Of course, within coordination. Okay, so that's the statement. And the proof uses some complex analysis. It's basically a version of what's known as the algebraic theorem. The way it comes in as follows: you just consider the difference of the two correlation functions, which is given as this object, where the powers of e's are coming out by the action of h on these states. That's how you get the powers of e. And now you can expand this correlator by inserting a complete set of energy eigentrates in them, which gives you some expression like this. And then what you can argue is that because of these particular setting outside these correlation functions, you can argue that these functions will be non-zero using the algebraic theorem. That is, you can argue that this kind of thing is non-zero, and therefore the only way in which the difference could be zero is C1 equal to C2. Hence, if these coordinators are same, then C1 is equal to C2. I've not gone through the technical step of algebraic theorem. So what we've shown is that if you have two-way functions which solve the Wheeler-Dirichlet equation in AES, and they coincide maybe boundary and an infinitesimal time interval, then they would coincide everywhere else.
What example can we think of equation where you are calculating suppose the correlation function of the same operators in two different states? So for example, here let's go back to the previous step, the previous one. So here your claim is equal. So the correlation of the same operator in two different states, right?
Yeah. I mean the same operator, of course, M, P, and N. They'll find that these are same for a large number of M.
Yeah. And the claim is that if this correlation function is same, then the states are same.
If these correlation functions are same on the same time band. Yeah. Of course, if they're same across all entire light crossing time, then it's a trivial state.
Yeah, that is what I was trying to think is that you think of a simple quantum mechanical situation where you calculate the correlation functions of same operators in two different states and you impose the fact that they must be equal, then the states must be equal.
Oh, yeah.
Is there a situation where there can where the states may not be equal in a simple quantum mechanical situation?
Yeah, just a simple example I started with is a demonstration of this. Just this particular example. You see, in this particular example, what I prove for you is that by measuring HOI in the state psi to determine what f of r was. But if you consider cross correlator, that is to determine HO2 in the state psi.
But then there is a different operator.
No, what I'm saying is this. So let me just now it's exactly what here. What I mean is this: if you have psi1, state psi2, then I'm going to measure the expectation value of. I'm going to measure the expectation. There's HO1 in psi1, then psi1 with HO1. So this is inside. The operators are HO1 and HO2.
The same
In the same state, sorry. And I'm also going to measure HO1 and HO2.
That is fine. What I am saying is that you measure each O1, you calculate the matrix element of psi1 and psi1, calculate the matrix element of each O1 between psi2 and psi1.
I'm just coming to it. So next I'm going to, as I said, I'm going to do 4 measurements. The next one is going to be this. So this is the same set of operators, but in 2 different states. What I'm saying is that this will give you f of r. This guy will give you f of r. But these both will give you 0.
No, what my question was, suppose you have a situation where you are measuring HO1 between psi1 and psi1 and psi2 and psi2.
Okay, this, yeah, so it's 1 and 3.
First and third case.
Yeah.
And you are if these two results are matched, these two results are same, then isn't it trivial that psi1 and psi2 should always be equal?
No, you see, the reason what's not trivial is that.
Yeah, that is what that is.
Okay, good. So I should emphasize to that part.
Because probably in a simple quantum mechanical situation,
yeah,
because it is probably a trivial statement that if these are equal, then psi1 and psi2 must be equal.
Yeah, I'll tell you where's the non-triviality coming in, and it's basically coming in. The fact that it's d goes from 0 to epsilon. So
here it is not trivial because you are saying in a time band.
Exactly.
But probably in a quantum mechanical situation, probably it is ordinary quantum mechanics.
In ordinary
probably it is a trivial statement.
Not really, right? Because you see, like, okay. So for example, if you're finding that these correlation functions, just I1 or psi2, are equal across all of pi, which is basically pi plus is less, then of course that's true. And then there's nothing non-trivial about it. Then there's just saying that instead of using a basis which is expanding fields in the bulk, we're just using a basis on the boundary. It's like the H cable. So here it's non-trivial because I'm saying these correlation functions match in this time, in the same time window epsilon.
Then the states are equal throughout the.
Exactly. I'm saying that if
it is not only equal in the thin time band, but it's for all time.
Exactly. That's the same. So in a sense, if I find that these correlators, where these correlation functions itself are measured in this state, are measured in this small time band. If these correlators are equal, then the states are the same. By states are the same, I mean these correlators are equal in all times. That's what the non-triviality is. And that's basically a notion of allowability that the boundary, like all information, is actually available from the boundary. Okay. So just to conclude the second part of the talk, the two-way functionals will solve the availability equation in ADS. One side may be boundary and then 20% time interval, then you put inside everywhere else. Okay. So now there are of course many natural extensions to consider. I don't know how much of this is actually possible. One thing is to try and derive the entanglement wedge reconstruction, some version of it using formalism. One more thing is a de Sitter space, which I know my friends are working on, but it's probably not a statement which is as strong as an ADS flat space, but it's still interesting by itself. Then some special cases of ADS2 and ADS3, which we don't know much about as of now. Something which I've been trying to do for the past 1.5 years on black holes, which is simple now, but it's quite literally extending all of this when you have black holes present. By which I mean instead of building states on top of the vacuum in ADS, you build states on some black hole solution. And then how much of this connects with the usual notion of class space allowability or celestial allowability we talk about? It's not quite clear, and many other dimensions which we worked on. And thank you for your attention.
Thank you very much, Chandramoli. Very nice talk. Any questions? A lot of questions now.
Just go to the slide where you said that excitations in the that is triangle red diagram. Yeah. So this is your Minkowski and Minkowski space, the causal diamond structure, right? So in this case, where is your I mean how you get the excitation? Why are you excited? In the bulk or in the boundary?
Oh, good. Thanks. So, yeah, sure. Clarified this before. Actually, the way I'm quantizing everything here is in a description that Ashtekar gave us years ago. It was the asymptotic quantization paper. But simply because the bulk doesn't have a very good description in quantum gravity because of the fluctuations and so on. So I'm using two facts. The first fact is that any excitation which is in the bulk, yes, black space, and it only consists of massless. All of this excitation has a one-to-one mapping with an excitation on either the future boundary or the past boundary. Like I could have also said the past boundary. In this case, I'm looking at the future boundary. So a state that you would have considered as something like this. Therefore, d r d omega, let's say on the t equal to some t naught slice, I might as well have just written it as an excitation at null. This function is slightly different. Let omega d omega. This is one thing that I'm using. If you only have massless particles, then instead of representing the state in the part, you can also quantize. You can do basically.
That means that capital and that psi, that state psi lives in the bulk.
Correct. I could have mapped it to the bulk as well. I could have also mapped it
And
to the
the
bulk.
phi is living in the boundary.
No. So this phi of r that I'm looking here, this phi of r is only.
It is in the bulk. Okay, so psi is in the boundary.
No, you see, psi doesn't have a location.
Okay.
Because psi is not dependent on space. Psi is found out of an object which is integrated over all of R. Psi is what the wave function. So I'm saying that you could have represented psi in two ways. One way by only using bulk excitations, and then by using what's known as the HKLL procedure, you could have also reconstructed it in terms of previousness or all over spectrums. So this is an integral all over spectrums. Then the non-trivial statement is that I'll be able to decode these functions by making measurements as characteristics.
Seeing that the energy is quantized in this picture. So is there any need for length quantizations or something like that?
I mean, an energy quantization, I just mean I need to use this H. Iota.
I was just asking because some quantum gravity model, they actually say that have the discrete space-time motions or
Oh, good. You're asking that energy.
yeah,
No.
that analogy, I'm asking that.
No. So okay, good. That's a good question. So this energy quantization I'm seeing is totally different from that energy quantization. So this, in fact, the energy quantization that I talked of is not even present in class space. Because in class space, energy has a continuous value. The continuous energy at least, yeah, which is usually the usual notion. The energy being discrete, what I talked about was only in ADS. So if you just take a scalar field, you just solve for the scalar field in the bus, you could have done it with any spin. You solve for the wave equation, you post derivative boundary conditions. So you will find that the spy actually has two modes, one which falls off as 1 by r, as you take r tends to infinity, and another which grows with I think it's delta minus sure, but anyway, another mode which grows with r, and this delta is something that's it's some expression in terms of your dimension. And if you set this guy to 0, that is, you use normalizable boundary conditions, and you use derivative boundary conditions where this is the boundary value, then you would find that you would have to quantize the energy of the field. So if you impose derivative boundary conditions and you use smoothness of the field and so on, you find that energy gets quantized as delta plus L into L plus D minus 1 plus 2n. Maybe getting the factor of 2 wrong somewhere, and there's also factor of space. But this is the quantization. This the energies of the field gets quantized just because of smoothness.
This is a quantization of energy of the matter field that you have.
Yes, and now by this, yeah, one second. Energy of the matter field is getting related to boundary value. And that's actually this can even be seen classified.
This your phi is basically that side. Right? So you're using
my phi is just a scalar field. The psi I is psi I looks sorry, so psi I that is written looks like the creation operators acting on e power minus.
This phi is a matter field, right? Phi is a scalar field. So what you are quantizing is the energy of the matter field.
Also H like this H. It can also be the H.
Yeah. But then what is this interpretation for this psi I on which this H delta acts?
Oh, so that
this is the wave function for the gravity field.
Wave function for it can also be a scalar field as well. You might as well set the transverse traceless part to 0. Then the energy is captured by the trace of the transverse part. So
Yeah.
So they just do that. Really, but what I mean is, if you have, I wrote down Hij in terms of the longitudinal and the transverse parts, and I further divided the transverse part into 2 terms. So one was the transverse traceless, which I'm calling as the gravity part. And the other thing, which is only the trace of the transverse part. So it's just 1 degree of freedom. And that 1 degree of freedom is the energy. So you can have excitations where this is set to 0, but you don't have any transverse traceless, but you cannot set this to 0 if you have matter fields in the bound. Because the value of this guy is determining the energy of other things in the bound, which is basically this equation. So this H I've written here could actually reduce to just Hij. So I mean this is
Like you are saying that HIJT that is related to values of the scalar field, matter field.
exactly, yeah. One simple analogy of this is just your electric flux. But when we know that this E dot ds is equal to just F0I. That's what EI is. So in some case, let's say when AI is 0, then sorry, A0 is 0, then this would basically reduce to derivative of AI. So in a sense, the boundary value of AI, which is the left hand side, that's related with the charge of the matter field inside. And here the charge is basically expressed.
But what about when you don't have any matter field?
If you don't have matter field and you don't even have HTT, then you might as well set HT equal to 0 and so on. That's if you don't even have HTT. Like if you only have graviton, or if you only have gravity, and
Pure gravity, no matter field.
okay, then you just have HTT. You just set this like 0. That's fine. 0 and this part is purely coming from your by expanding your external equations and that's the transverse traces, which are the real gravitational reasons.
Which are the real gravitational reasons. No. Why I'm interested in that, pertaining to Ushmita's question also, that in that case, then I will be really able to measure or find the energy eigenvalues of the pure gravity. Because we are basically having the equation H delta acting on some psi I, yes, some function of, this is the gravity wave function of, and that is equal to something. And in that case, we were putting on the graviton degree of freedom, the physical degree of freedom, and we were saying that let me have only HT, which depends on the matter field. Yes, these are completely matter.
No, sorry. HT has both matter and HTT.
Yeah. HT has both matter. So now if you switch off the HTT, then it has only matter.
Only matter.
It is only matter. But if I switch off the matter, then HT will depend only on HTT. The energy will depend on
what number plate. If you have a graviton gas, then
and then it will be something like we are really looking at the energy eigenvalues of the quantum gravity theory.
Up to perturbation theory.
Perturbation. Okay.
I mean, like I said, this equation will just get modified by a spin factor. Forgetting whether it's plus S or it's plus S by 2. That would be the energy. That equation is well known. So in principle, you could also have string extensions.
But how do you tackle the question that Ushmita asked? That is there any length quantization or?
So this energy quantization is not like the energy quantization which people in quantum gravity have. This energy quantization is true even if KFP works with it. True. So that's totally different from the length quantization. Gravity where X and X don't compete, like Xi and Xj don't compete.
But the way you are quantizing the theory here,
Yes. This is a semi-classical.
By imposing the Hamiltonian constraint, you are elevating the Hamiltonian constraint to an operator and then saying that it acts on psi to give you 0.
Yes.
So that is the way people do in quantum gravity also. Of course, the standard way.
Where of course trying to do all orders.
The boundary condition, like a box like boundary condition, in which they quantify that. the length quantization, people often use that it's a particle in a box, and they use the boundary condition that phi is at both the boundary is 0. So from there they say
But
that the
that will not
space
give
is
you
quantized.
length quantization, so that is phi. That's a matter field. But the way you are quantizing the theory is actually completely similar with what people do in loop quantum gravity. And there you have the concept of length getting discretized and everything comes out.
Actually, the way I'm quantizing is very similar to QFT index.
True. But the same thing is done in loop quantum gravity. You
Yeah,
just have the Hamiltonian constant and you put that H size 0.
So that's probably to more higher orders in quantification, maybe non-quantification. In this case, all I'm doing is summing.
Or maybe it will not come out from here. Maybe.
Yeah,
They do something more on top of that.
I was just asking from a very general perspective, as we do even from a GOP theory.
Anyway, we can now we stop the session and the speaker. Very nice talk. And question we can have.